Thank you. Thank you. Okay, so how do we go about solving something like this? Second order differential equation. That's right. So we got a second derivative here, right? Now remember, solving a differential equation means undoing the derivative by anti-differentiating, right? Okay, but a second derivative is a derivative of a derivative. Okay, so does it make sense that to solve a problem like this, we're going to have to do 2 layers of anti-differentiation? Okay. All right, so what do we do if f double prime, the second derivative, is given to us? What integral do we set up to anti-differentiate the first time? Suggestions? And another way of saying this would just be the derivative with respect to x of y prime equals that, right? So how could we write that in differential form? Okay, multiply by both sides by dx, so we end up with the derivative of y prime equals the quantity x cubed plus x dx. And now I can just anti-differentiate to undo the derivative, right? You don't have to show that step, but that's, you know, that's how we're thinking about it. I would say you could really just jump straight from here down to there, right? And so we could probably just write this as f prime of x equals the antiderivative of the second derivative function, right? Does that make sense? And we could jump straight from there, you know, down to this layer. Is everybody okay with that?
Absolutely.
Okay. So what do we get for an answer?
1/3. Oh, definitely. 1/4 x.
Okay, good. Plus
1/2 squared.
Okay. Plus, I'll call it C1, some constant, right? Okay, but look, we have some initial conditions, don't we? Okay, we have 2 of them this time. We've got one for the value of the first derivative at 0 and one for the value of the function at 0. Which one's going to be important to us here? Yeah, first derivative, right? So we know that at this point right here, we know that f prime of x equals x to the 4th over 4 plus x squared over 2 plus c1. But we know that when x is 0, f prime is 6, right? Say it again. One more time, so I can't just.
I said C1 is going to equal 6.
Oh, right, exactly. There you go. Perfect. Yeah, exactly. Yeah, you're right. So when we plug that in down here, f prime of 0 then is going to give us all the x's become zeros, right? So we get 0 over 4 plus 0 over 2 plus c1, and that's equal to 6. So there's c1. Good. Okay. So we can plug that value back in right there, and now we end up with a first order differential equation that we can solve. Right? It's like a new problem. So now we've got f prime of x equals x to the 4th over 4 plus x squared over 2 plus 6. And we've got that other initial condition that I'll rewrite because it's way up there. F of 0 equals 10. Okay, so now what? anti-differentiate, right? So f of x equals integral of all this stuff. So what's that give us? So what's the first term going to give us if we take the integral? Okay, so I get the 1/4 times x to the 5th over 5. So I just end up with x to the 5th over 20, yeah. Plus yeah, I got the 1/2, and then the integral of x squared, remember, is just x to the 2 plus 1 over 2 plus 1, so x cubed over 6 plus some constant, but we have our initial condition up here, right? When x is 0, this value of this function is 10, and so if we evaluate this thing at 0, that goes to 0, that goes to 0, that goes to 0, and it equals 10, so we know the value of our second constant. And so the function is, then, we're done. F of x equals x to the 5th over 20 plus x cubed over 6 plus 6x plus 10. There's the function. We solved it. Okay? Make sense? Okay, so what I want to leave off with here is kinematics, right? So I left you with a puzzle the other day. If we were able to, and we could, if we set up an inclined plane and we did some measurements, we could come up with a pretty accurate estimate of the acceleration of gravity, the uniform acceleration of gravity on the surface of the Earth. If we did that, we'd find that g is approximately equal to actually negative 9.8, right? Yeah, that's lowercase g just means acceleration of gravity.
Oh,
okay. Negative 9.8 meters per second squared. Negative just because it's going down, right? That's the positive vertical direction. So, okay, so can we come up with the kinematics equations from that?
I bet you we can.
I bet we can too. I bet we can. In fact, we could do this. We could even do this. We don't even need to relegate ourselves to just considering gravity. If we take any constant acceleration situation, we know the acceleration's constant. Remind me real quick, what is the relationship between position, velocity, and acceleration? So if we say that s equals position, so position is going to be s of t. Say we know that function. What is velocity? Do you remember?
S prime.
It's right. Good. S prime, or as we say, we'd say s dot, I guess, because it's t. It's ds, dt, or s dot, right? Okay. What about acceleration?
That's double
It's
dot.
double dot.
Yeah. So it's going to be the second derivative of s with respect to t, or s double dot. Okay. Which is also, by the way, v dot, isn't it? V to t. Okay.
Oh, yeah.
Now, you physics types, you've worked with kinematics, right? A lot of the kinematics equations, I'm just going to bring this up real quick. A lot of the kinematics equations refer to things like, for example, v naught. What's that? Okay. Good. So we have things like v naught and s naught. Not to be confused with snot. It's a different retard. But yeah. Okay, so we'll get back to that. But so how can we do this then? If we know that the acceleration is constant, right? So if we know that the v dt, right, ds, the second derivative of s with respect to t, no matter how, either way you want to write it, it doesn't matter. Let's write it this way, how about? Equals a, where a is a constant, acceleration is a constant. How could we solve that differential equation? Doesn't look too hard, does it? I could write it in differential form if I wanted to, right? So dv equals what? Yeah, a dt. If I anti-differentiate both sides, wouldn't I just get v equals the integral of a dt? But we said a is a constant, right? So the a could even really even pull that out of the integral. What's the answer? What's the integral of dt? T, isn't it? It's really just a 1 dt, and the derivative of what is 1? Well, t, right? If t is the variable that we're differentiating with respect to, right? So this is just equal to at plus some constant. Oh, but that's kind of a bummer. We got a constant there. Okay, but you told me up here just a second ago that v naught appeared in your kinematics equations, and that was meaningful. It represented the initial velocity, right? So why don't we evaluate our answer at 0? Okay. So v of 0 then would equal a times 0 plus c naught. That term goes away, doesn't it? And what's the meaning of that constant then?
That is the,
Yeah, so the constant really does mean something. It's the initial velocity, whatever that might be, right? And so that brings us to the first layer. This is a kinematic equation too, isn't it? So we end up with velocity equals acceleration times time plus v naught. Okay, you might remember that one. That's how you get it. We could go another layer though. We know that velocity is the s dt, right? And so if we wanted to write another differential equation in terms of position, right? Multiply both sides by dt to put it in differential form. Take the integral, and we get s equals the integral of at plus v naught dt. Okay, what's the solution to that one? Here, go to the next page. Okay, so what's the solution to that one?
time multiplied by your velocity.
Yeah, so we got acceleration is a constant, right?
Yes.
So we could take that out front, but what's the antiderivative of t to the 1? T squared over 2, right? So I've really then just got 1/2 times a t squared, right? Are we familiar? Plus, what's the antiderivative of some constant times 1 dt? So v naught dt would just be and what's the, remember that's like v naught could be 2, for example. So what would be the antiderivative of 2? 2t, right, in this case. Because the t is going to drop off when you differentiate, right? So v naught t, but then we got to include some constant. Okay, but we can do the same trick. If we just evaluate this whole thing at 0, get 1/2 A times 0 squared plus V naught times 0 plus C2. And so what's the meaning of our second constant? What's that mean, S of 0? S is just position, right?
So that's
Well, okay, but it's S stands for position, right? But if I'm evaluating it at 0, what kind of, specifically, how might we describe that position? Yeah, initial position, yeah.
That's just half.
And so we end up then with S of t equals 1/2 AT squared plus V naught T plus S naught. And I think the way you guys, I'm not totally sure. Some books deal with this differently. I prefer that expression of the equation, but a lot of books, and I think yours does this, right? They just say S minus final position, or position minus initial position is displacement. Is that right? And so they just call this delta S. Is that how your book said it?
Yeah.
I think so. Yeah. I don't know if they use the same symbols, or, and these ought to be vectors too. Okay, make sense? All right, how about that? Okay, so.
Were you going to a lab?
Yep.